Okay, this is the beginning of our uh, muscles and levers, I guess lecture part, because we are going to talk about levers and how muscles are involved in your lever systems in your body. So let's just read on through here. It says skeletal muscles produce movement by exerting force on tendons, which in turn pull on bones. Muscles will attach to bones by their tendons. The muscle fibers themselves are in the middle of that structure, and the tendons are the dense connective tissue which is going to attach to the periosteum of the bone. So muscles attach to bone by their tendons. Well, the muscle origin is the stationary point of attachment of a muscle tendon. So that part of the muscle that attaches to the bone that does not move when the muscle contracts. Like if you look at your upper arm, your biceps muscle, well, bicep means two heads, and the two heads are going to attach up on your shoulder. And when that muscle contracts, your shoulder does not move, but your forearm does. So we look at the next word, the muscle insertion, the movable point of attachment of the muscle tendon. So look at your arm, bend your arm, feel right where your elbow bends, and you'll feel a tendon there. That tendon is going to your radial tuberosity on the radius in your forearm. So when that biceps muscle contracts, your origins stay put. But the insertion, which is on your radius there, the radial tuberosity, that does move. It pulls your forearm up to flex your forearm. Now the muscle in between the tendons is called the belly. It says the portion of the muscle between the origin and insertion, also called the gaster. Gaster means belly. Like gastrointestinal, that's your belly region. When we do these problems, we're going to do some problems in just a minute. You have to know the parts of the lever system. So a lever may be defined as a rigid rod that moves about on a fixed point called a fulcrum. And you see here that the bone is going to be a little rod here, a lever. The joint is called the fulcrum. And there's an F, like a little triangle with an F in it for fulcrum. That's where the joint's going to be. The resistance, a force to overcome. That's the mass or the weight that you have to overcome, like lifting that bag of sugar or that 5-pound weight. That's the resistance. And the effort, the force needed to overcome the resistance. It's applied at the point of insertion. So when the muscle contracts, the effort's applied at the insertion. And it's called effort. It's going to be one direction or the other, whichever direction is pulling, either down or up. How levers are classified. And we're going to see that in just a minute too, but we're going to look at 3 class levers. First class, second class, and third class levers. So it's going to involve the position of the fulcrum. Where is the joint? You know, the joint of this lever system. Where's the effort being applied? And where is the resistance? So the locations of those 3 parts determines which type of lever you're working with. Equation used to solve the lever problems. This is the only equation that you need to use to solve these problems that we're going to talk about. And so I have to define the wording here, and we'll see it on a slide in just a minute. We'll see these distances. EA stands for effort arm. Now look at the definition. The distance from the effort, that's where the force is being applied, to the fulcrum, to the joint. So it's the distance between the joint, the pivoting point, and where the muscle's applying the effort. E stands for effort, the force needed to overcome the resistance. How much effort is needed to overcome the resistance, that mass you're trying to lift, let's say. Resistance arm, RA, the distance from the resistance, that's the load, to the fulcrum, the joint. And then the resistance is a force to overcome, like a 5-pound weight or something that you're trying to lift. Now, we're going to look at some problems to work. And here's the first class lever. This is how it's set up. It looks like a seesaw. So it's set up like a seesaw. The joint's somewhere in the middle between the resistance and the effort. So there's your fulcrum, the joint. There's your resistance, the mass to overcome, the weight to overcome. And there's the effort, the direction that's being applied on the seesaw to overcome the resistance. Body example, the occipital condyles articulating with the superior articular surface of the atlas. Well, the fulcrum is going to be right here. The top cervical vertebra is called the atlas, and then the condyles of your occipital bone, the occipital condyles are going to articulate there. So that's the pivot point. That's where the joint is. So it says occipital condyles articulate with the fulcrum. The muscles of the neck exert the effort to the nuchal lines on the back of the occipital bone. If you remember, the superior and inferior nuchal lines on where the occipital bone is in the back are going to apply the effort to overcome your head trying to fall forward. Now, you know that's true because if you have any kids or you've watched somebody fall asleep, when they fall asleep, their head is the resistance and it falls down. So when they wake up, the effort of the muscles around the back of the skull on the occipital bone, those nuchal lines, see the effort's applied this way down to raise the head up. So you can, you're conscious and you're looking around your environment. So first class lever is like a seesaw. Second class lever, set up like a wheelbarrow. Here's the fulcrum here at this end. The resistance is between the fulcrum and the effort. Now the foot is a good example of this. The ball of the foot is the fulcrum. When you stand up on your toes, you say you're trying to get a little height to look over like a fence, you would roll up on the front of your foot. The resistance is the weight of the body exerted on the talus of the foot. If you remember, your tibia is going to be coming down on top of your ankle bones. Well, the top one there is your talus bone. That's going to be the resistance, all your weight. And the effort is applied to the calcaneus bone. This would be by the gastrocnemius muscle of the calf, your calf muscle. So your calcaneus is back here, and your Achilles tendon is here. It goes up to your calf, your gastrocnemius. And when you stand up on your toes, this gastrocnemius pulls up, and you roll up on the ball of your foot, the fulcrum, and you're lifting all of your weight by doing that. So this is why wheelbarrows are used in construction. You have a wheel up here at the front. The load that they're hauling is in the middle somewhere, and the effort is applied to the handles. The worker has to just lift the handles. So you can overcome a lot of weight with this type of lever, second class lever, the wheelbarrow. Third class lever, example is the arm. Now it says the object in your hand is the resistance. So your hand's out here where R is, and you're holding like a ball. The effort applied to the radial tuberosity of the radius. Well, I told you what that was a minute ago. And then your elbow here is the fulcrum, the joint. So this one is shaped like your arm. Your elbow's here at the joint. Your effort's being applied by your biceps brachii muscle on the radial tuberosity, and the resistance is what you're holding in your hand. So let's look at some problems. Here's problem 1. Which class lever is this an example of? Well, I've got the answer here because it used to be a PowerPoint that you would have to figure that out yourself. But it's a third class lever because it's like one like you were lifting a minute ago. Your elbow's here, the resistance is there, and your effort's applied at the radial tuberosity. So this is a third class lever. So here's how the problems will go. I can give you any one of these 4 values here. What I've given here is resistance arm is 12 inches. Okay, so that's from the resistance to the fulcrum, 12 inches. The resistance is 8 pounds. That's over here. It's 8-pound resistance. The effort arm is 3 inches from the effort to the fulcrum. It doesn't matter that the resistance arm and the effort arm overlap. Doesn't matter. So how much effort is needed to overcome that 8 pounds, given all the parameters here? This is not hard because I told you that you have an equation. Resistance arm times resistance equals effort arm times effort. I gave you resistance arm, it's 12, times resistance, that's 8 pounds, equals effort arm, 3 inches, times effort, which you don't know. So you just solve the equation for x, and you're going to, it'll be like 12 times 8 is 96, divided by 3 equals the effort. It's 32 pounds. So the math is not real hard on this. You just have to solve for the fourth number. The fourth number. But again, I could give you any of those four. It doesn't matter. This type, you see that it's set up like a seesaw. The fulcrum is in between the resistance and the effort. So it's a first class lever. Now we see here, I gave you 4 things here. I gave you the resistance arm is 2 inches. That's the distance from the resistance to the fulcrum. The resistance is 12 pounds. The effort arm is 3 inches. Well, this is not set up exactly like that, but that would be 3 inches here. How much effort is going to be needed to overcome the 12-pound resistance? You set it up the same way. Resistance arm times resistance, 2 times 12 is 24, equals effort arm times effort. Effort arm was 3 inches, and effort is unknown, so you solve for the unknown. So you divide this side by 3. 24 divided by 3 is 8 pounds. It's going to take 8 pounds to overcome that resistance of 12. Now problem 3, this is an example of a second class lever, like a wheelbarrow. And so I gave you, I didn't give you effort this time. See, I don't have to give you effort. I can give you any one of these 4. So I gave you resistance is 12 pounds. There it is, 12 pounds in the middle. Effort arm, 3 inches. Effort is 8 pounds. So you put the equation together. Resistance arm, you don't know, times resistance, 12, equals effort arm, 3, times effort, 8. So 24 divided by 12 is 2 pounds. So I'm going to 2 pounds to lift that 12-pound resistance. That's why, again, wheelbarrows are so big in nature, or in construction, in construction. But you can see all these lever systems in your body.